Hello, my name is Sekiyama, Division of Materials Physics, Graduate School of Engineering Science, Osaka University, Japan. In this movie, I would like to show that by using the time-dependent perturbation theory in quantum mechanics, where the interaction between the electron and photon is treated as a perturbation, the optical transition probability is derived, which is called as a Fermi's golden rule. I hope that the audience has already learned the light quantization and the interaction Hamiltonian of electron with photons explained in the movie entitled as Quantization of Light shown here. Please enjoy this movie. Here we mainly consider this term, A.P term, and within this lecture we neglect the third term, two-photon process. Okay? From now, I explained physics of the one-photon process for electron. In other words, what happened for electron under the quantized electromagnetic field. In order to solve such a situation, we need to use the so-called time-dependent perturbation quantum theory. Time is divided into before irradiation and after irradiation. That is the meaning of the time dependent. Of course, before irradiation, here we set t of 0 is the starting time of the irradiation. Now, before irradiation, of course, A is 0, therefore the A.P term becomes 0. In this case, of course, the energy of the photon field is also 0. Then, in this case, we can express the total Hamiltonian H as electron Hamiltonian He. And here we assume that we can solve the Schrödinger equation of the electron Hamiltonian He and get the result of the ground state A with the energy of large EA. Namely, we assume that we can use this relation. This ket A stands for the one electron state. Then we start irradiation under the incident photon. Then the Hamiltonian is expressed by using this one, the sum of the electron Hamiltonian, photon Hamiltonian, and interaction terms A.P. Then we suppose that the electron Hamiltonian and that of photon field is much larger than the interaction term H1. H1 shows a relatively very small effect compared with He and H photon. And further, we suppose that incident light is highly monochromatic with a photon energy of h bar omega. Then we treat H1 A.P term as perturbation. After the irradiation, the time-dependent Schrödinger equation is expressed by this one. So since this is the total Hamiltonian, and we need to pay attention that the psi, state psi, is a direct product of the electron and photon field. So here the A stands for the electron state and N omega stands for the state of the photon field with the number of photon with energy of h bar omega as N omega. At just the starting of the irradiation, number of photon is incident light intensity. Just starting irradiation, nothing happens. The electronic state in the ground state, but the irradiation is going on. The total state can be slightly changed. We consider such a situation. Of course, in most cases, nothing happens. That means state is still in state I. But very small probability, we can see another state expressed by the J, defined by the direct product of the another electron state, AJ, and another photon field state is the number of photons is N2 prime. Then we express the state psi as a linear combination of the state I and state j as this one. So at first, we need to consider all possible states of j. And Ci and Cj stand for the time-dependent coefficient. Then we put this state psi into the Schrödinger equation. But since Hamiltonian of the electron and photon field is well understood that EI is the total energy in the initial state with electron energy EA and the number of photon n omega. Therefore, this relation is satisfied. I found a typo. Here is J. Also for J state J, this relation is satisfied. Then when we put the psi, state psi into the time-dependent Schrödinger equation, we obtain this relation. On the right-hand side, only the H1 term remained. Other term is cancelled out because the sum of the time derivative gives this term times the energy EI and this term times EJ. So such a term is cancelled out. Only the term related to the H1 must be considered. Then the next task is to solve this differential equation. Still rather tough, but it's possible under the approximation. Now, we consider the one of the excited state F as the direct product of the one of the electron state B and one of the photon state n omega prime. Then we multiplied this state F from the left-hand side to all the term. This is another state from the electron state A. Therefore, the inner product of F and I is 0, mutually also normal. And inner product of the F and state J is expressed by using the Kronecker delta. That means by multiplying the state F, only the state F becomes finite in the left-hand side. Then we get this differential equation. When we solve this differential equation, the situation is equivalent to solving the time-dependent Schrödinger equation, but still rather difficult because of the presence of all terms of the time-dependent Cj. So it's still tough. So this is a differential equation for the coefficient Ci, Cf, and Cj. There are so many time-dependent terms. Then we use approximation. So at first, I said that H1 is perturbation. That means probability of the interaction is very small. But even the probability is very small, the number of electrons is of the order of 10 to 20 or 10 to 23rd or something like that. That means even if the probability is 10 to minus 6, number of the excited electron is more than 10 to 10 or 10 to 15 or something like that. So we can observe such kind of electron. Anyway, we consider that Cf except for Ci is very small. Further, at the starting radiation time, only the coefficient Ci is 1 and other coefficient is 0. And the radiation is going, the Ci is reduced from 1 but nearly 1. The other term Cj is could be finite but far from 1, like this one. Then we neglect the second term and we set this term as 1. Then we can obtain Cf by the integral of the right-hand term. We obtained this one by simple calculation. This one is time independent, as I explain later. Then we can obtain this result just after the integral of the exponential function, like this one. So this term, the square of the CF, coefficient CF, stand for the kind of the transition probability from the state I to state F. Now we calculate the transition probability square of CF. So this is obtained from this result, like this one. And further we calculate, and then we get this result. By using the nature of the sines and cosine function, we get the coefficient like this one. Then I continue to evaluate the transition probability CF. I neglect the last term, but finite. This amount is smaller than 1. So we can continue the evaluation of this term. The situation is like this. All the electrons in the ground state and the stable state. In other words, the total electron energy is minimum. That is electron state A. And state B, only one electron is excited, and this electron is in the high energy level. Electronic state is like this one. And when we remind that the quantized vector potential is expressed like this one. This bold small e stands for the polarization direction, not the charge. So this is an interaction term A dot P. Importance is that this R stands for the coordinate of the electron to be excited. Therefore, interaction between the electron and photon can take place. We put this form into here, then we get this one. So this P stands for the momentum of electron, and this K stands for the wave vector of incident light, and this R stands for the coordinate of the electron to be excited. Then we can further calculate. So the total initial state I is expressed by the direct product of the electron state and photon field, and final state as a direct product of the electron state B and photon field N prime. Their energy is just simply expressed by the EA plus N omega H bar omega and EB plus N omega prime times H bar omega. In the final state, the number of photons could be different from the initial state. Then we continue the calculation and evaluate this term. So we can calculate like this one. These terms tell us a very important thing. One is this one. One excellent thing is that by this calculation, we can divide into the electron part and the photon part. So this is just photon part. We quantize the light by the same manner of the harmonic oscillator. Therefore, the nature of the annihilation and creation operator is the same as those for the harmonic oscillators. When we remember the nature of the annihilation operator for the harmonic oscillator, we can understand that this term is finite only when the n prime is n minus 1. That means this is the one photon is absorbed. And second term is a counterpart. In this case, this is a creation operator of photon. Creation means the number of photons increases. That is emission. Also in this case, n prime must be different from the n omega by 1, but n plus 1. This is the emission part. Therefore, this interaction tells us that one photon absorption and one photon emission. But in the case of the ground state A, its energy EA is minimum. in order to obtain the emission, as I explained later, one photon energy must be added in the photon field. But as I discussed later, that is not possible due to the energy conservation. Therefore, now we consider only the absorption process. Then, here, as I said before, the number of the photon n omega prime must be the same as n omega minus 1. Otherwise, this term becomes 0. Then we consider the energy difference between the total initial state and the total final state, like this one. So this is the energy difference of this one and this one. Since the number of photon in the final state, n omega prime, is the same as n omega minus 1, the energy difference between these is expressed like this one. And here we define the h bar omega AB as the energy difference between the EB and EA. Then we can express the energy difference of the total state as this one, because this is a one photon absorption process. Then we go back to the transition probability CF, like this one. In the previous slide, we get the coefficient is expressed as this one, and this is also equivalent to this one, since omega Fi is omega AB minus omega. Okay? So then we considered how large or how small this amount. And it is known that this is a so-called zinc function, sin x over x. So it is known that time is going on, that this function makes a very sharp peak at omega AB. For instance, from the time of t0 to 2t0, this peak becomes larger and larger. Instead, width becomes narrower and narrower. And also it is known that this integral becomes alpha pi. I show this calculation. So in order to consider this integral, we need to consider this complex function. And integral path is described by these red curves. Since this function has a singular point on the real axis, point of x0, but we avoid this point at this integral. And within this integral path, this function is holomorphic. Therefore, this integral itself becomes 0. And integral over this path becomes also 0 when the radius becomes infinity. Then we need to consider the integral along the real axis and this one. So this is a clockwise direction. Then we need to consider residue of this function at the x0. Then we get this relation. Then we can understand that integral of this function along the real axis is proportional to the residue at this point. So we get this relation. Then we only consider the real part of this function and we get this relation. And finally, we get this result. This is the same as this one. Okay? Now we know that this integral becomes alpha pi. So then we go back to the evaluation of this function. So as I said before, this function shows a very sharp peak at omega AB when the time is going on. That means this function can be approximated as delta function times alpha pi, like this. So when we set alpha as t over 2 and x minus x0 as omega minus omega AB, this function can be evaluated as a function proportional to the delta function of omega, linearly proportional to the time, like this one. When t is much longer, So that means within a very short time, this approximation is not available. But time is going on, we can use this approximation. That is uncertainty principle between the time and energy. So time is very short, the energy is not conserved, but time is so long, becomes longer and longer. Of course, the energy must be conserved. This approximation tells us these things. Then we can evaluate the transition probability as this one. This is called as Fermi's golden rule. And further, we put this one in the last slide. I calculate this term. Then we get this result. This formula tells us many things, but one very trivial thing is that this one. Transition probability is proportional to the number of photons and irradiation time. That means probability is proportional to the total amount of the irradiated photons. Okay? And the second one, this is important. The transition probability becomes finite only when the photon energy is just the same as the energy difference of the state A and state B, energy conservation. So this energy conservation can be applied for this condition, but in most cases we can apply this relation. Only when we use a very short pulse laser, laser light is no longer monochromatic. We can understand that transition probability is evaluated as this form. Then we need to consider this term. So we need to discuss next. This is very important for one-photon process.